way to write the hypothesis is talking about the association. So my null hypothesis would be that there is no association between education and vote. That whatever relationship, whatever differences I saw in my sample is just due to randomness of the sampling method and not actually due to there being a cause and effect relationship or even just an association between the variables. Alternatively, my alternative hypothesis is that there is an association between education and vote. Now, some books write this differently. Some books will write it as education and who you vote for are independent. Alternatively, their alternative hypothesis would be education and who you vote for are not independent. Now, before we proceed with the hypothesis test, we need to make sure the conditions to run a hypothesis test are met. Our conditions to run a hypothesis test are that we took a random sample, and most, if at least not 80% of the expected counts are greater than 5. If this is true, we can run a chi-square test for independence. So, to find the expected counts, we need to take the column total times the row total and divide that by the table total. So, when we look at this, we see that here there was 180 people that participated in the survey that had a high score or less. We can see that 480 voted for Clinton, and we can see that our table total is 1001. So this would be, to find the expected counts for this group, we take 180, multiply times 480, and divide by 1001. And that would give me this box right here. Next, to find this, I would need to do 470 times 180 and divide by the table total, which is 1001. And I would do that for each box to find the expected number of votes each candidate would get for each group. Now I went ahead and did this already in StatCrunch, and you can see that I got 86.31, 84.52, 9.17. So to do that in StatCrunch, you go to Tables, Contingency, with Summary. We pick our our columns. We pick our rows, and we click on Expected Counts and hit Compute, and it will do all those calculations for us. So here's what was observed, here's what was expected, and that's how I got this table down here. So we need to find the test statistics, set your graph, and find the p-value for the chi-squared test of independence. Now, chi-squared is our test statistic, so to find that, we need to follow this formula. Take each observed count, subtract the expected count, square it, and divide by the expected count. Our degrees of freedom equals the number of rows minus 1 times the number of columns minus 1. So here's what StatCrunch gave me. I do 81 minus 86.31, 92 minus 84.52, I do 7 minus 9.17, and I go through and I do that for each of these values. Now, once I have all those, I square those values and divide them by the expected. Now, when I do that, I will get what we call the chi-squared test statistic. Now, if you look at StatCrunch, whenever you make a contingency table, you can see right down here it does that calculation for you. So if I did all of those calculations, I'd get 12.96. Now, next, I'm going to place 12.96 on the chi-squared distribution. Now this chi-squared distribution comes from the degrees of freedom. So since I have 4 rows and 3 columns, I have 6 degrees of freedom. which means this peak right here is at about 4. Now when I calculate that, I get a p-value of 0.0436, which again is all done for you in StatCrunch. I just want to show you the theory behind it. Now we write our conclusion. When we assumed the variables were independent, we found the probability of getting a chi-squared more extreme than the one from New York Times sample was 0.0436. Thus, the probability of the difference in our survey responses happening by chance is unusually small using a significance level of 0.05. We reject the null hypothesis that who you voted for was independent of education level. We have enough evidence to support the claim that education and who you voted for are not independent, that there is an association between the two variables. Now, it's very important that just because we are able to reach this conclusion, that we realize that through this hypothesis test, we have not concluded a cause and effect relationship. An association does not necessarily imply causation. There could be lurking variables that affect who you vote for more than education. There could be a variable that affects both your education level and who you decide to vote for. And so it's very important not to try to draw a cause and effect relationship from this data set. Some rules about the chi-squared distribution. The notation for chi-squared distribution is Greek, and it comes from chi-squared. It's spelled C-H-I, but we do pronounce that as chi. The degrees of freedom change the shape of the distribution. The curve is non-symmetrical and skewed to the right. The test statistic for the test is always greater than or equal to 0. And the peak is at degrees of freedom -2. Here's the graph that I wanted to show you. So when degrees of freedom equals 2, we get a chi-squared distribution that looks almost exponential. So it looks like this. And when chi-squared the degrees of freedom equals 24, we get something that starts to look normal. And really, for large sample sizes of 40 or more, the chi-squared distribution doesn't really look that different from the normal distribution.